Greetings everyone, I'm Razieh Izadi. I have a PhD in mechanical engineering and I'm a researcher at Sapienza University of Rome under supervision of Professor Patrizia Trovalosci. Here I'm glad to present to you a work on mechanical characterization of carbon nanotube using molecular dynamics simulation and adapting micropolar theory to model the observed atomistic responses. In the present work, I have the honor to collaborate with Dr. Tuna and Professor Trovadoshi from Sapienza University, Dr. Fontuzzi from University of Bologna, and Dr. Gavonlu from Shiraz University. Carbon nanotubes, also called CNTs, have many innovative applications due to their peculiar physical characteristics. However, their smart application requires a deep understanding of their properties. With atomistic simulation like molecular dynamics or Monte Carlo simulation, we can provide a deep insight in nanoscopic phenomena. However, severe computational expenses are imposed on the problem, which limits the size and time scale of the studied system. Continuum models calibrated through atomistic simulation or even experiments offers a solution for preserving the accuracy of simulation while exploiting the efficiency of continuum description. Some observation in atomistic simulation or actual experiments suggest a size dependency in CNTs. We believe this size dependency originates from the comparable internal structure in CNT, that is the carbon-carbon bond length to its overall diameter. Since classical Cauchy theory cannot take into account the internal structure of a material to model CNT and describe its size dependency, we have adopted non-classical theories that can preserve the memory of materials' internal structure through internal scale parameters. Using molecular dynamic simulation, two kinds of deformations, that are bending and torsion, are applied on two sets of 8 armchair and zigzag single-walled carbon nanotubes with mean diameter ranging from 6 to 16 angstrom. The aspect ratio is fixed at 5, however, we have checked the independency of our results to the aspect ratio. Then, to apply a loading that resembles pure bending, we should avoid a spurious axial strain. So we have proposed a new method in which after every small incremental rotation of both ends, the two ends come closer to each other at a calculated value so that the arc length remains equal to the initial length of the tube. Then, using the linear part of the moment curve versus bending angle, the bending rigidities are determined, from which the bending modulus are calculated. By comparing the bending modulus for different CNTs, we could see a size dependency in the bending modulus. This size dependency cannot be described with local and classical theory because it predicts a constant bending modulus for different diameters. Since micropolar theory has been successfully used to describe a wide range of materials with internal structure like brick masonry walls, particulate composites, porous materials, in our works we check the applicability of this theory and also coupled stress theory to model the size dependency observed in CNTs. You could see the governing equation for the case of micropolar theory in the picture. Then we try to solve the problem of pure bending of a circular cylinder in the frameworks of micropolar, a constrained form of micropolar theory that is a bit simpler, and the modified coupled stress theory. The relation for bending modulus then is determined for each case, and you could see in the picture the relation for bending modulus for the three theories. Then, to determine the constitutive parameters, a nonlinear optimization approach is adopted to minimize the difference between the bending rigidities obtained from MD simulation and that of continuum description. We adopted also the following inequality constraints that originates from the principle of non-negative energy and also a criterion related to the thickness of nanotubes. The results show that the size dependency in bending modulus is best captured when using micropolar theory. Micropolar theory inherently can account for relative rotations that is related to the skew-symmetric part of a stress and strain tensors. So here we conclude that we have asymmetries in a stress and strain tensors that can be best captured by micropolar theory. And almost identical predictions are provided by modified coupled stress theory and constrained micropolar theory. Even though the results are not as good as micropolar theory, but sufficient and valuable results are provided considering their oversimplified formulation. And as you see, an evident deficiency of classical theory is observed. We have come to an interesting result, and that is the value of the internal scale parameter, that is the bending characteristic length, in the problem turns out to be directly related to the carbon-carbon bond length in CNTs, which is around 1.4 angstrom. Then we focused on the torsional deformation of CNTs, and we performed torsion on the same set of armature and zigzag nanotubes with different diameters. We found the torsional rigidity, and from that we calculated the shear modulus of these CNTs with different diameters. Again, you could see a size dependency in shear modulus that cannot be predicted by classical theories. Analogous to the bending case, the problem of torsion of a circular cylinder in the framework of both micropolar and coupled stress theory is determined. You could see the displacement field, the strain and curvatures calculated by the kinematic relations, and then the strain and curvatures are substituted into constitutive and equilibrium equations to solve the problem. Finally, we could find the shear modulus relation in the micropolar and coupled stress theory. Then, through an optimization approach, we minimize the difference between the MD results and theoretical predictions to find the micropolar or coupled stress theory parameters for armature and zigzag CNTs. You could see again that micropolar theory can better capture the observed shear modulus obtained from molecular dynamics simulation. The unified material length scale is also relevant to the hexagonal structure for both armature and zigzag CNTs. We checked the results and compared the results of torsion and bending deformation, and we see that a consistent results are obtained from these two deformations. This proves the competency of our method, which is independent of the loading protocol. During this work, I was receiving a research scholarship from Sapienza University of Rome with financial support of Italian Ministry of Education, which is highly acknowledged. Thank you so much for your time and your attention.